Hello, here we have another helpful hint. Chapter 11, problem set 1, problem 14. All right, we have a ball that technically is shot from point P. It's going to roll without slipping, go up a ramp onto a plateau and off the plateau and land at distance D from a point directly below the right left of plateau. So what is the speed that the ball had initially that got it to, project to distance D? So they're giving us the distance D, the height from where the ball left. So therein lies the part of the answer to this problem. So we're going to work backwards. So let's get started. All right. So I guess I want to call it, part one to this whole thing. Uh, use the downrange distance equation to determine what the initial horizontal speed was when it left the plateau. All right. So you know the downrange distance, and then you can figure out the time that it took to reach the ground from that downrange distance. Since it's being projected horizontally, you can use the special version of that equation, 2y over g is the sake of the square root. And then the y is equal to h2. All right, so let's get that out of the way. And you're going to get a velocity, in and around 1.05 meters per second, just so you can compare that with your calculations. So you need to get that out of the way. So let's apply conservation of energy and specify what state 1 and state 2 are. All right. State 1 is where the ball is shot. It's going to be the beginning. And then state 2 is where the ball leaves the plateau. Okay, state 2. Now that we know what the velocity is. Okay, let's develop that relationship. So state 1, okay, so taking accounting of all the energy at state 1. So we have kinetic energy of rolling or rotation plus kinetic energy of translation. Okay? And we're lower than we're going to end up. So there's no gravitational potential at the beginning. So those two energies are going to result in energy at state 2. So conservation of energy. At state 2, the ball apparently is still rolling without slipping. So it's got, here, let's go, let's subscript those 1. It's going to have kinetic energy of rotation plus kinetic energy of translation. And it's going to be above where it started. So we're going to give it some gravitational potential energy. All right, so that's essentially what you have. I'm going to list the equations that each of those energies represent. So the kinetic energy rotation, 1/2 I omega squared plus 1/2 mv squared is equal to 1/2 I omega squared sub 2 plus 1/2 mv squared. Okay, that's the velocity once it leaves the plateau. Okay, that's what we calculated over here. So we'll call that v2. And then plus mgh1. Okay, mgh1. So that's important to this. So it actually had to convert its energy at state 1, move up a height h1. So don't get that h2, h1 confused. The h1 is for the calculation, how long it's going to take to reach the ground when projected horizontally. Okay? I'm going to leave it at that. Know your magic substitutions. Omega is related to speed over r. Okay, and that's going to be the line share. That's the radius of the continuous body, that mass. It's a solid sphere, so let's put that out there. The rotational inertia for a solid sphere is 2/5 mr squared. Okay, and in this case, little r is going to be equal to big R. All right, once you substitute all that stuff in, things are going to cancel. You're going to get a mass in every term. that goes away. Let's see, our meters. Okay, it looks like we got centimeters, so make sure you convert the centimeters to meters just to be consistent so there are no goofs. And here's the velocity, just so you can compare your answer. This is the velocity that the ball was shot with, okay, at point P. So the velocity at P is 1.34 meters per second. So that's what you should get. All right. Now, this is a helpful hint. I spent some time putting this video together. So, I just want to help you out. So do what you can to fill in the blank and the space in between my hints. All right. So using conservation of energy, state one, where it started, state two, where it's going to end up at the point where it's going to leave the plateau. And then it's all yours. All right. Have a good evening, or day for that matter. And you're welcome.